Okay, so let me restart. Welcome again to this last session of PODC2020. And the first speaker is Doron Mukhtar, and the talk is entitled Single Source Shortest Path in the CONGEST Model with Improved Bound. Please. Doron? Doron? Oh, yes. Do you hear me? Can everybody, Yuval, do you hear me?
Yes.
We hear you.
Doron is telling me that he doesn't hear me.
It must be a problem on his side. I mean, we hear you perfectly well.
Okay, do you hear me?
Yes.
Yeah.
I can't hear you.
Doron?
Okay, in this lecture, we are going to talk about the problem of computing shortest paths from a single source in the CONGEST model of this-world computing. This talk is based on joint work with Shiri Chechik. Recall that in the CONGEST model, we present a communication network by an undirected graph, where each vertex corresponds to a device in this network, and each edge to a communication link between them. The vertices in this network can communicate with their neighbors by sending small messages along these edges, where this is assumed to be done in synchronous rounds. In each round, each vertex first receives the messages that were sent to it in the previous round, performs some local computation, and then sends possibly different messages to some or all of its neighbors, where the size of these messages is assumed to be bounded from above by an order of log n bits, where n is the number of vertices in the network. Initially, each vertex knows the directions and or the weights of its incident edges, if such are given, and we assume that this information does not affect the communication in any way. That is, we assume that the communication is always done in a bidirectional manner and always in discrete rounds. This is just an input for the network. In the distributed single source shortest path problem, we have a single designated verse S, which we call the source. And our goal is to devise an algorithm that each vertex is going to execute in parallel so that by the end of the computation, each of them will know its distance from this source. Our aim is, of course, to find the fastest possible algorithm, where in this model, the complexity of such algorithms is measured by the number of communication rounds that they require in the worst case. In this talk, we focus on weighted and or directed graphs. For this type of graphs, a lower bound of almost square root of n plus d was shown in this work, where d is the diameter of the underlying communication network. The upper bound for this problem has been improved in a series of work, starting with that of Elkin, which holds for weighted and undirected graphs, and finally getting to this bound, which holds for directed graphs with non-negative integer weights. We managed to improve this bound by devising a new randomized algorithm for solving this problem for the same class of graphs using no more than this number of rounds. To obtain this result, we first devised a new procedure for computing distances in virtual networks, which works best when the weights of the graph's edges are relatively big. Then we use this procedure to compute distances in general networks. In the case of unweighted directed graphs, we follow a known framework to compute distances in parallel. In a very high level, the idea is to sample a set of skeleton nodes, perform an ongoing BFS from all of them, and then construct a suitable overall network in which we compute distances by repeating this scheme again and using the approved procedure. For the case of weighted directed graphs, we follow the same framework of Foster and Nagukake, by relying on a no reduction, it's enough to design an algorithm for computing approximate distances that preserve a certain form of the triangle inequality for the graph's edges. Our main contribution is a new method to compute such estimations efficiently. This was achieved by introducing a new weight modifying technique, which we call iterative gradual rounding. To summarize, we have reviewed in this talk the current state of the art for the SSP problem in the CONGEST model of distributed computing. Many problems are, of course, left open. Perhaps the most important one is to close the remaining gap between these two bounds. Other interesting directions could be, for example, to find efficient deterministic algorithms for this problem, or to find faster algorithms for more restrictive classes of graphs, for which weaker lower bounds are known, such as the graphs of constant underlying diameter and so on. So that is, and thanks for listening.
Thank you, Doron. And is there any question?
Can you tell us what is known for the deterministic case, please?
I don't think that he can hear us, so maybe we can type. But
Yes, maybe typing is a good idea. He continues to write to me that he doesn't hear, he cannot hear.
So I cannot hear you, but I see them the question in the chat. Okay, so for the deterministic case, then I think that for the case of directed graphs, then I think that nothing is known. And I think that also for the exact undirected weighted graphs, nothing is known.
Okay, let's thank Doron.
The case of all pair shortest path was almost resolved in a recent paper that showed that it's possible to solve this problem in order of n rounds.
I guess we can take the other questions offline, since there is also this issue with...
Well, we don't know how to remove this multiplicative factor.
Okay, so I guess we can switch to the next speaker. The next speaker is Arnold Filster, and he will talk about distributed construction of light networks. And if I invite the next speakers to enable the camera, it would be nice. Thank you.
Hey, so can you hear me?
Yes.
Yeah, so this is also a talk about the distributed CONGEST model. So in this work, we talked about light spanners. So a spanner is just a subgraph that preserves pairwise distances. So here the stretch is kind of the approximation factor of the distances. And usually people care about sparsity, that they want the spanner to have small number of edges, or lightness. So this work focuses about lightness, which is the ratio between the weight of the spanner, which is simply the sum of the weights of all the edges in the graph, divided by the weight of the MST, which is in a sense the minimum weight possible to get a finite stretch. So previously, people constructed spanners in various settings, but I guess the most relevant works are by Althoff et al. And Nielsen, who showed like almost optimal or optimal trade-offs between stretch to lightness or sparsity. The most relevant work in the CONGEST model is by Boussois-Nassen, who show almost optimal spanner in the sense of sparsity, and constructed it in K rounds in the CONGEST model. Our first contribution is a construction of light spanner with almost optimal parameters, both in lightness and number of edges, and is also almost optimal up to this 1/4K plus 2 factor, the number of rounds by a lower bound by Sarma et al., who showed that even to compute an MST, one must use square root n plus d number of rounds. The second contribution of this paper was SLT, or shell light tree. So a shallow light tree is some combination between shortest path tree and MST. So you're given a root R, and the goal is to both approximate all the distances to R. This is for every vertex V1, the distance in the SLT will be at most alpha times larger than the distance in the original graph. And secondly, you want the SLT to be light. And the result of Kuller et al. Is a trade-off of 1 plus epsilon stretch and 1 plus 2 over epsilon lightness. And you can choose the epsilon. This is known to be tight. So before, nothing was known in the CONGEST model, and we construct almost optimal SLT. So we have this 1 over 1 of 1 here instead of 2, and the number of rounds is square root n plus d, which is again optimal by the same lower bound for MST by Sarma et al. Thirdly, we constructed spanners for a doubling metric. So here a metric has doubling dimension d if every ball of radius r can be covered by at most 2 to the d balls of half the radius. And here Borderline et al., improving many previous results, constructed a 1 plus epsilon spanner with lightness epsilon to the minus d and epsilon to the minus d times n number of edges, which is asymptotically optimal. And our contribution is the construction of the spanner in the CONGEST model. When we have the lightness and the number of edges is just multiplied by log n compared to the optimal possible, and the number of rounds is again square root n plus d times some second order terms. However, there's no lower bound here, so possible to get much better. And the main tool to construct this double matrix was the construction of a gamma beta net, which is in a sense a set of points which is both gamma covering. Each vertex has a net point distance with gamma, and all the net points are beta separated. That is, the distance is at least beta between any pair of points. And previously, Luby showed a KK ruling set, which is in a sense a KK net in unweighted graphs, which took him a K log n CONGEST rounds. So we kind of generalize it to weighted graphs, where we get for every gamma and beta such that gamma is between beta and 2 beta, one can construct a gamma beta net in square root n plus d times second order terms number of rounds. And this is also tight in the sense of number of rounds by a kind of reduction to MST. So the open questions left are several. So first, for general graphs, we would like to remove this 1 over 4k plus 2 in the number of rounds. Secondly, this kind of k factor here. So we know how to remove it in a sequential model, but it will be nice to remove it in the CONGEST as well. And I guess the most interesting case is for k equal log n, where in sequential case, it's known how to get log n spanner with constant lightness. Well, here, this result only will give you log n lightness. So the second question. Thirdly, the one I mentioned about the SLT. So here, the optimal one is 2, while we have asymptotically 1. Yeah, of course, in the doubling case, it will be nice to remove these log n factors, but more importantly, to show any lower bound, because Sarma et al. Does not hold here, or get better running time. And the final question I would like to ask and see resolve is some metric approximation of the TSP problem. So here in the sequential, Christofides give us 3 halves. Recently, there's been even some slight improvements. However, in the CONGEST model, so one can get 2 approximations using the MST, but nothing better. That's it. Thank you.
Thank you. There is already one question that asks if these algorithms are deterministic or randomized.
So they're all randomized.
Okay. Any other question?
Yes, I have a question, please. Hi, Arnold. Is there an application of the shallow light? Like, is it used in?
You mean the
Give
CONGEST
an
model?
example of where it is
General.
used. Excuse me?
In general, I mean, in CONGEST model, we don't have applications currently, but for general settings, so I at least use it, for example, to construct so yeah, so I think a bit. Yeah, I used it to construct, for example, a spanner with constant average distortion and constant lightness.
Okay.
So in a sense, this is like an MST. You can construct in a sense a single tree like MST, which has constant average distortion, which is like nice, not for a single vertex. And I guess like, this paper has quite a lot of citations, I guess at least 80, so I guess there are more.
Thank you. Thanks.
Hey, so maybe I missed it, but I think all of the works is in the unweighted setting, right?
No, weighted setting. I mean,
Oh,
unweighted
okay.
is, I mean, it's much, weighted, everything is essentially known by Botswana and similar. The whole point that's kind of in the weighted setting, you have quite a difference between the graph you work on in the CONGEST model, the network graph, and the actual graph, the metric you compute in distances. And this is the reason for the square root n. Otherwise, you can get with much faster.
Okay, thanks.
And if there are no other questions, thank you again, Arnold. And the next talk is entitled Simple Deterministic Constant Round Coloring in a Congested Clique. And the speaker is Peter Davies.
Hi, yep, so I'm Peter Davies. I'll just share my screen in a second.
Yes, Arnold? Okay, great.
Okay, so yeah, I'm Peter Davies, and this is about coloring in the congested clique with Arta Chumai and Marav Pata. So yeah, we're in the congested clique despite sneaking into a congest session. So we have our input graph, and the computation is done on the input graph, and the input graph has n nodes, m edges, and maximum degree delta. But our communication doesn't have to be done just over the input graph edges. It can be done over the entire clique. So any pair of nodes can communicate in synchronous rounds, like in CONGEST, and they still have this bandwidth bound, so they can send log n bit messages. But actually being able to communicate between any pair of nodes makes the model quite different. And it actually is more like parallel computing. It's equivalent to linear space MPC under some restrictions. So the results I'm going to show you actually work also in linear space MPC. I elaborate a bit more on this in the long talk, but for the purposes of this talk, the main upshot of this is that I'm going to ignore the fact that computation is done in nodes of the graph and instead talk about machines. But other than that, it won't make much difference. So we're looking at the delta plus one coloring problem, the classic problem where we have our input graph, and each node in the input graph is given as input a palette. Actually, for delta plus one coloring, these are all the same, but our algorithm also works with delta plus one list coloring where they can be different and given as input. And each palette contains enough colors so that even nodes with the maximum degree have at least one color that can't be used because they only have degree delta and they have delta plus one colors, so you can always do a greedy coloring. And our goal is then to find some such coloring where we don't have any two edges which have their endpoints the same color. So that's the problem. It's been studied quite a lot in a variety of distributed parallel settings, and also as a benchmark for de-randomization, which is also what we're doing here. So in the congested clique, what can you do? So if you just start off with the basic randomized coloring algorithm where you just, with probability of half, have each node randomly pick a color, try to color itself, talk to its neighbors to see if it's successful. If it is, you remove it and say that the neighbors can't use the color. In congested clique, you can run this in log delta rounds because after that, your graph is small enough to fit onto a single node. And then Marav in 2018 de-randomized something along these lines to get a deterministic algorithm with the same running time. But actually, randomized coloring algorithms, there are ones with much better running times. So in the local model, Chang Li and Petty's algorithm got this log star delta plus some deterministic running time on instances of size log n, but that doesn't really apply in congested clique. And this was used as the basis for a succession of much faster randomized algorithms, so culminating in a constant round algorithm last year. But it didn't lead to faster deterministic algorithms because this Chang Li and Petty's algorithm is quite resistant to any kind of de-randomization. It's very difficult to see how to make it deterministic. So basically what we did was come up with a different randomized algorithm which we could make deterministic to give us a constant round deterministic algorithm, both of delta plus one coloring and delta plus one list coloring. And so I've been speeding through this up to this point because I'm going to try and give you the whole randomized algorithm at least on the next couple of slides. And then to see how it's de-randomized, you can either take my word for it or look at the full talk. So how does our algorithm work? Well, we have our input graph here. And all we do is we want to map all the nodes into different buckets so that we can look at them separately. So kind of like a divide and conquer type thing. So we just randomly send the nodes into these buckets. The number is polynomial in delta, but beyond that doesn't really matter. And we want to be able to look at these separately, which means we have to give them different palettes of colors to use so that there are no collisions between them. So we also randomly partition the colors into the buckets. But the important part here is that we can't put the colors into all the buckets because then a lot of the nodes won't get enough colors to color themselves. So we leave one of the buckets without colors and just put the colors into the other buckets. And that means that most nodes then get more colors in their bucket than they have degree in their bucket, so they can color themselves greedily. For nodes for which that's not true, that don't get enough colors or that have degree too high, we just put them into a bunch of leftovers to solve afterwards. And then on everything else in the buckets is good. And then we just recursively run on all these buckets. And as I said, the point of doing this was that we can now run on these in parallel because they're using completely disjoint color palettes. So we run on these in parallel. We can collect them into nodes of the graph in the congested clique and solve them separately. And we recursively apply the algorithm to solve them. Then we can just update the palettes and recursively solve them. The bucket that didn't get colors, so to begin with, their palettes are just what they were before this partitioning step. After updating, they remove all the colors that were used by neighbors in the blue buckets, and then they still have sufficiently large palettes to recurse on. And finally, we just show that this leftovers, so the nodes that got too high degree or not enough colors, that's a very small graph. The induced graph on that is less than linear size. So we can just, again, collect that onto a single machine and solve it straight away. We don't have to recurse on that. So that's the whole randomized algorithm. And yeah, I kind of cut out a lot of other stuff to fit this all onto one slide and give it to you in the short talk. And the reason we made this algorithm, we can show it's a constant round randomized algorithm, but there was already a constant round randomized algorithm. But because our only randomization here is used for this partitioning stage, and actually you don't need very much independence at all to do this randomized partitioning. You only need a constant-wise independence. We can de-randomize all the randomness, which is just partitioning the nodes and the colors, in only a constant round overhead using standard de-randomization techniques, bounded independence hash functions and the method of conditional expectations. And that then gives us a constant round deterministic algorithm. So yeah, that's all I wanted to fit into the short talk. So thanks for watching.
Thank you, Peter. Are there any questions? Yes, very nice talk indeed. And Jennifer is saying nice and accessible talk.
Oh, good. I was worried I was doing it at double normal speaking speed. But
can you say something about computing the chromatic number in congested clique?
Short answer, no, not really. I mean, here obviously we're doing delta plus one coloring, so we're assuming. I mean, you can always delta plus one color. It's possible you could color in far fewer colors, but no, we haven't really looked at computing the actual chromatic number. Even delta coloring is a much harder problem.
Okay, any other question? This was a question from Seri, by the way. How large is the constant, Yannick asks?
So I didn't really try to minimize the constant. I don't think it has to be large. Currently it is large because I didn't try to not make it large. It's something like, I don't know, there was a 6 to the power 9 in there somewhere, I think, which is probably the main part. But I expect if you actually tried, you could make it not huge. Yeah.
How much of the congested clique bandwidth are you using here? For example, could you solve order of log n or order of square root n many coloring instances in parallel in order of 1 rounds? Yuka asked this question.
What do you do here? So I think you only use, I think, an arbitrarily small polynomial for checking the partitioning and running conditional expectations. And then the only time you need a linear amount of space is for solving the individual instances, which are done on single machines. So possibly you could run more in parallel. Yeah, I think maybe you could possibly run a polynomial amount of instances in parallel, but I'd have to check. a lot of the details.
Okay, I guess we can take the other questions if there are any offline. And thank you again, Peter.
Okay, thanks.
The next speaker is Caleb Robel, and he will talk about efficient and simple algorithms for fault-tolerant spanners.
Okay, let me share my screen really quickly. All right, can everybody see the screen? Yes. Okay, great. So yeah, so I'm Caleb Ravel, and I'll be talking about efficient and simple algorithms for fault-tolerant spanners. So I'll begin with like a formal definition of what a spanner is, and I won't go too into that as they've already been discussed in the session. So let G be a graph. We say that G prime, a subgraph, is a T-spanner of G if all pairwise distances are preserved up to some multiplicative factor T, which is known as the stretch of the spanner. For an example, we can consider the following graph. The subgraph to the right is a 3-spanner of it, since all pairwise distances are preserved up to a multiple, no more than 3 times the shortest path distance in the original graph. A sort of similar idea is the idea of fault-tolerant spanners, and we define them as follows. So let G be a graph. We say that G prime, a subgraph, is an F vertex fault-tolerant T-spanner for G if we can remove up to F vertices from G prime and G, and what remains of G prime will still be a T-spanner of what remains of G. And so the idea here is that your spanner property is robust to failure against up to F vertex failures. And this can be, you can define edge fault tolerant spanner similarly, but in this talk, I'll be focusing on the vertex fault tolerant case. And so once again, for example, we can consider this familiar graph, and the subgraph to the right is a 1 vertex fault tolerant 3-spanner, because notice that if I select 1 vertex to remove from both graphs, whatever remains on the right will still be a 3-spanner of whatever is remains on the left. So we might want to look at how much it costs us or to add this sort of fault tolerance property to a spanner. And so to do this, what we do is we look at the following theorem of Althoff et al., which is sort of the fundamental theorem of spanners. And what they show is that given any natural number k, all graphs will have a 2k minus 1 spanner with big O of n to the 1 plus 1 over k edges, and this bound is tight, assuming the Erdős-Girth conjecture. And so now that we have a tight bound on spanner size, we can look at, oh, how much do we have to pay in order to add this sort of fault tolerance property? And so there's been a line of work over the past decade or so looking at this. So Chechik et al. Gave the first construction of fault tolerant spanners for general graphs, and which is followed by Dinesen Krautkramer. Then in 2018, Bodwin et al. Gave a greedy construction algorithm, which was shown the following year by Bodwin Patel to actually build spanners of optimal size, and this optimal sort of size bound was big O f to the 1 minus 1 over k n to the 1 plus 1 over k. So we have a greedy construction algorithm which builds spanners of optimal size. So let's take a look at that algorithm. And so if we look at this algorithm, we'll see that we have this sort of, in the main loop here, we have this if statement here, where what we're doing is when we consider each edge for adding to the spanner, we check if, in the spanner we've built so far, if that pair of vertices, the spanner property is robust against failure of up to F vertices. So the sort of naive approach to checking whether or not a given pair of vertices, the spanner property is robust for a given pair of vertices, takes exponential time. So what that means is that this algorithm for constructing optimal fault tolerant spanners will take up exponential time. So that sort of raises a question, is there an algorithm which produces optimal or near optimal fault tolerant spanners in polynomial time? And by optimal, we mean optimal in sort of this fault tolerant threshold F. And so we sort of, in our paper, we sort of answer this question in the affirmative by giving a polynomial time algorithm which builds spanners which are only a linear factor in k away from the optimal size bound of Bodwin and Patel. And I'll first go over how we do this in the weighted case, and then I'll very, very briefly describe how we can in the unweighted case, then I'll describe how we can generalize our results to the weighted case. So we first look at this problem known as length-bounded cut, which we define as follows. So given a graph G, two vertices U and V, and a natural number T, we want to find the smallest subset of vertices which, when removed from our graph, break all UV paths of length less than or equal to T. And so we claim that if we can solve this problem, we can sort of determine whether or not there exists a fault set which breaks the spanner condition for a given pair of vertices. And so originally, our if statement, which says if there exists a fault set which breaks a spanner condition for a given pair of vertices, we replace that with if there exists a length 2k minus 1 cut of size less than or equal to f. And so a length 2k minus 1 cut here would be a set of less than or equal to f vertices, which breaks all length 2k minus 1 paths between u and v. Unfortunately, it turns out that this problem, length-bounded cut, is NP hard, so we can't do this. We can't solve this problem. We don't know how to solve this problem efficiently. So what we do is we design a T approximation algorithm for this problem with T equal to 2k minus 1. So with this approximation algorithm, we can determine whether or not we have to add an edge to our fault-tolerant spanner while we're constructing it. And this gives us a construction algorithm in the unweighted case. Since we are using an approximation algorithm to determine whether or not an edge is necessary, we end up adding some more edges than we need, but we can modify the analysis of Bodwin and Patel to show that this only adds a linear factor of k in the size. Now, in the weighted case, sort of the first thing we might want to consider is whether or not we can just take this approximation algorithm and use it to determine whether or not an edge is necessary when building spanners for a weighted graph. But it actually turns out that efficiently approximating length-bounded cut in the weighted case is an open problem, and there's no known sort of way of doing this. So it turns out, however, that we can actually reduce constructing fault-tolerant spanners in the weighted case to the unweighted case by considering edges in increasing order of weight, and then just kind of blindly running our unweighted fault-tolerant construction algorithm. So because of this, we don't actually need to look at the weights except for in this pre-processing step where we sort edges in non-decreasing order of weight. So before I sort of conclude, I'd just like to go over some of the key ideas that I brought up. So spanners are just sparse subgraphs that approximately preserve distances in an original graph. Fault-tolerant spanners have the additional property that the distance approximation will be preserved after either a few vertices or edges fail. In this paper, we provide a polynomial time construction algorithm for fault-tolerant spanners in the unweighted case by replacing an exponential time subroutine for finding fault sets with a polynomial time approximation algorithm for this problem length-bounded cut. And then we show that the weighted case, constructing fault-tolerant spanners in the weighted case, can actually be reduced to constructing spanners for unweighted graphs, by considering the edges in non-decreasing order of weight. And this leaves a couple of open problems. So like at the time of submission, an open problem was, can we remove this linear factor of k from the size of the spanners our algorithms build to get optimality? Well, this problem was actually since been solved by Bodwin, and Rebel, and you can see our results on arXiv where we provide polynomial time algorithms to construct optimal construct fault-tolerant spanners of optimal size. Another open question is, can we improve the edge fault-tolerant bounds for stretch greater than or equal to 5? So all the bounds I mentioned previously were for the vertex fault-tolerant case, and in the edge fault-tolerant case for stretch greater than or equal to 5, there's currently a gap in the upper and lower bounds, which would be nice to close. And sort of a final open question is, can we find polynomial time algorithms for near optimal or optimal fault-tolerant spanners in the CONGEST model? We currently don't have any such algorithms, and it would be nice to have some. But yes, thank you. That's all I'd like to talk about right now.
Thank you, Caleb. And there was a question, but you already answered to it. that
Yes.
what is known about the distributed algorithms for solving this kind of fault tolerance spanners.
Yeah. Yeah. Yeah.
So are there any other questions?
Yes. Could you say something about the follow-up? I mean, what is the algorithm? How it is different?
So the algorithm that we use here sort of is just kind of like a natural extension of the greedy algorithm of Althofer, where you just, you consider the edges in non-decreasing order of weight and then check the spanner condition. So the follow-up algorithm works. Well, actually, I can. The follow-up algorithm works kind of by you sort of by. Well, I'm not sure if I can give the best explanation in the time that we have right now. Maybe I can like send a link to the archive paper so you can take a look at it and get like a more detailed explanation. Yeah.
That's a good idea.
Yeah.
Any other questions? And if not, then thank you again, Caleb. And the next talk is about distributed approximation on power graphs, and the speaker is Shreyas Pai.
Hope you can see my slides.
Yes, everything is fine.
Okay. Thank you for the introduction. The title of this talk is Distributed Approximation on Power Graphs. This is joint work with Ruben, Karen, and Yannick from the Technion and Sriram from the University of Iowa. I am Shreyas Pai. In this paper, we consider optimization problems in the CONGEST model. Just to recap, the CONGEST model is a synchronous message passing model where we are given a graph G as the communication network, and the nodes can send log n bit messages per neighbor per round. The central question we want to ask is what makes optimization tasks easy or hard in the CONGEST model. Minimum vertex cover is an example of an optimization problem. I call this problem G-MVC throughout the talk. In this problem, we want to find the smallest set S of vertices such that at least one point of every edge in the graph is in this set. So in the CONGEST model, exactly solving G-MVC requires quadratically many rounds, n squared rounds. And a 2 plus epsilon approximate solution can be obtained in log delta over epsilon log delta rounds, where delta is the maximum degree. And the fastest known better than 2 approximation takes n squared rounds. And this is a trivial algorithm where you just gather all the input graph edges at a single vertex and solve it locally at that vertex. In this paper, though, we consider optimization problems on G squared. Here we are in the CONGEST model with communication graph G, but we want to solve the problem on the squared graph G squared. In G squared, there is an edge between two vertices if they are at least at most distance 2 in G. In this task is easy if we have unbounded messages, as in the local model. So congestion is the only issue that we can face here. And congestion, in fact, becomes a really significant issue because the communication network is G, whereas the input graph that we want to solve the problem on is G squared. So even learning all the incident edges of the input graph could require linear rounds in the CONGEST model, let alone solving a problem on G squared. So let's take a step back and see why do we even want to study power subgraphs. Turns out that a vertex coloring on G squared arises in applications like frequency assignments of radio networks. So here, if two neighbors of a vertex use the same frequency, then it leads to a collision at V. So for every two vertices at distance at most 2, we would want them to use different colors, that is different frequencies, so that there is no collisions when they communicate. Also, de-randomization techniques in the local model require computing network decompositions of G squared as an important primitive. And more importantly for us, trying techniques for solving optimization problems in G squared could help us in understanding how to solve optimization problems in G. So when we try to solve optimization problems in G squared, congestion becomes an issue where G squared's computing in G squared potentially suffers from a lot more congestion as compared to computing in G. But it turns out that G squared also has a lot more structure compared to G, which can be potentially exploited for designing faster algorithms. Let me give a small example of how we can exploit structure in G squared. It turns out that the set of all vertices forms a 2 approximate solution for minimum vertex cover in G squared. So we get a nice zero round 2 approximation algorithm for G squared MVC, where every vertex just joins the vertex cover. And in contrast, for G-MVC, we need more than a constant rounds for getting even a constant approximation. And this more than constant term is in this box here. So the main contribution in this paper is that we analyze the effect of congestion versus structure on 2 fundamental problems. The first is minimum vertex cover, which I call G squared MVC. And the second is minimum dominating set, which I call G squared MDS. At a high level, G squared MVC becomes easier and G squared MDS becomes harder than the state of the art for these 2 problems on G. So the 2 main distributed results in this paper are a deterministic 1 plus epsilon approximation algorithm for G squared MVC that takes n over epsilon rounds in the CONGEST model. And we show a lower bound of n squared rounds for any constant approximation less than 9 over 8 for G squared MDS in the CONGEST model. Let me relate these 2 results with the previous work. So for MVC, we know that exactly solving G-MVC requires quadratic rounds. And the fastest known better than 2 approximation takes O of n rounds. And nothing was known in the previous work for G squared MVC. And we give a 1 plus epsilon approximation algorithm in linear terms. For MDS, exactly solving GMDS requires quadratically many rounds. And the same paper also gave a linear lower bound for log n approximation for G squared MDS. Notice that for approximating GMDS, nothing better is known. And in this paper, we give a lower bound of n squared for a worse constant approximation for G squared MDS. But the lower bound is much tighter, much higher. We also show other distributed results like an n squared lower bound for exactly solving both the problems in the CONGEST model. And these lower bounds, along with the approximate MDS lower bound, is based on 2-party communication complexity reductions, like in the previous work. We also show some sequential results in this paper, like a polynomial time 5 over 3 approximation algorithm for G squared MVC. Notice that this is a better than 2 approximation algorithm. And we also show certain hardness results like G squared MVC and MDS are NP hard, no FP-TAS for G squared MVC unless P equals NP, and no better than log n approximation algorithm for G squared MDS unless you can solve NP problems in quasi-polynomial time. Let me end with some open problems for minimum vertex cover. So a big open problem is what is the complexity for 1 plus epsilon approximation in the CONGEST model for G-MVC and G to the R MVC for R greater than 2. Our algorithm only works for G squared. So this is an interesting question. And even getting slightly better than 2 approximation for G-MVC is a really interesting open problem. For MDS, on the other hand, can we get a quadratic lower bound for larger approximation factors? And also, can we extend it for G to the R for any constant R? Thank you, and I'll take any questions that you have.
Thank you. There is a question from the chat. Is there any lower bound for approximate minimum vertex cover in CONGEST in G? Not in the power.
No, this is a pretty hard problem. So nothing is known for constant, known for even 1 plus epsilon approximate hardness. We only know an n squared lower bound for exact, and only, oh yeah, for constant approximations, we do know the like the Kuhn-Moschi-Broda-Wattenhofer lower bound, which is I'm sorry, I got lost in my slides. Yeah. So this sort of lower bound we know for constant approximations in G, but nothing better than this is known.
Any other questions? If not, then thank you, Shreyas. And the next talk will be the last talk of the session and of the conference, and it will be given by Yuval Efron. And the title of the talk is Beyond Alice and Bob, Improved in Approximability for Maximum Independent Set in CONGEST.
So hi, the title was already said, and this is joint work with Ofer Grossman from MIT and Seri Khoury, who also helped with the slides, from Berkeley. So the CONGEST model was probably defined in this session like 5 times, so I'm simply going to skip this slide and go straight to max-IS. And well, in the max-IS problem, we are tasked with finding the largest independent set in a graph, where a independent set is some subset S of the vertices, such that each 2 nodes from the set are not connected by an edge. So for example, in this graph, this is a max-IS, and this is a max-IS. To give you some context about what is known for max-IS in CONGEST in terms of lower bounds, well, it is known that to compute max-IS exactly, one needs to spend a near quadratic amount of rounds. Furthermore, even to approximate max-IS within a constant multiplicative factor, one needs to spend a nearly quadratic amount of rounds. In this work, we employ multi-party communication complexity for the first time, in order to amplify the previous hardness of approximation result for max-IS, improving in both the approximation factor and the running time. So reducing from communication complexity is the technique that we are going to use. And it is worth mentioning that reducing from 2-party communication complexity is by now a well-known and standard technique for obtaining lower bounds for CONGEST. And it was used for showing lower bounds for all kinds of problems, such as subgroup detection problems, distance computations, spanners, and more. And well, many of these constructions, and in particular the previous hardness of approximation result, reduced from the set disjoint function, which is defined as follows: f of x and y, where x and y are binary strings, equals 0 if and only if for some I, both xi and yi are 1. So let us take a very quick look at the previous harness of approximation construction for max IS. You don't need to know much about this construction. You only need to know the following property: that if the sets are not disjoint, then we do have an independent set of weight at least L for some parameter L. But that's our disjoint. Any independent set is going to have weight at model minus D, where intuitively we lose these D nodes from the independent set in these gadgets here that I refer to as code gadgets. Well, what if we had more players than two? Could we maybe somehow amplify this gap and get a improved lower bound in terms of the approximation factor? I'm going to exemplify this by using 3 players, where you can imagine each 2 players here being connected precisely in the same way as in the two-party construction. Now, intuitively, what will happen here is that we are actually going to lose D nodes from the independent set for each 2 players here. So we are going to lose D nodes for A and B, we're going to lose D nodes for B and C, and we're going to lose D nodes for A and C. And again, intuitively, this is what allows us to get a larger gap between the solution value of maximum independent set, depending on the disjointness of the strings. I do need to be a little bit more precise here, because we are no longer in the two-party communication complexity setting. We're actually in the number in hand Blackboard model of communication, where players communicate by writing bits on a shared blackboard. And we're not using the set disjointness function. We're using the promise gap disjointness function, in which we are required to differentiate between the case that T strings are uniquely intersecting or are pairwise disjoint. By using this model, this function, and more players, we are able to show the aforementioned improved hardness of approximation results for max IS. So to conclude, this was the first application of multi-party communication complexity for showing congest lower bounds. So that's cool. Can we use it to maybe show hardness of approximation results for other hard problems, such as minimum vertex cover and minimum dominating set, which is precisely the problems that were discussed in the previous talk. Yeah, that's it, I guess.
Thank you, Yuval. Are there any questions? So what is the best approximation that for this problem that we know that has a running time that is much faster than this lower bound?
If by much faster you want something like polylog, then you can get a 1/delta approximation deterministically.
Okay.
If you want polylog, you can get a 1 plus epsilon times the delta approximation, but this is already randomized.
Thank you. So let's thank Yuval again. Thank you. And this concludes this session. Thank you all for your attention, and thanks again to all the speakers.
Thanks, everyone. That concludes also the whole conference, right? I would like to thank everyone for bearing with us in these difficult times. I'm not sure that Yuval is still here.
I'm here.
He's
Thank you very much.
Okay. Okay, this is my closing word. I'll let Yuval do another closing word. It was
nothing to add.
It was a new experience for us, for all of us. I think I thank everybody for helping with this, especially the steering committee, Jennifer and George Welsh, and Yuval for making the technology possible to facilitate this. in an unusual new form. I think we've learned a lot about how to run that in such a conference in our online world. And I think we can retain some of what we did for future conferences. Yeah, and the steering committee, of which I am part now, is going to look into this in the future. Okay. So thank you, everyone. That closes my contribution to this conference, and stay safe and see you. Looking forward to seeing all of you in real life pretty soon.
I just wanted to say thanks to everybody, all of the organizers, the people that submitted papers, the authors, and the program committee, and all the participants. I think it was a remarkably interactive experience, way more so than I expected. So thanks to everybody, and hope to see you next year, but maybe in person.